Hey, welcome back to Calculus. In this video lecture, we're going to take a look at section 3.4, the chain rule, and it's going to be the last of our differentiation rules. All right, so the goals of the lecture are written there. We can just kind of walk through them together like we usually do. First of all, I want to tell you when you use the chain rule, how to recognize when its use is necessary. So that'll be our first task. Then we want to talk about what the chain rule is and illustrate how to use it with several examples. Depending on how long this video gets, I won't give a proof of the chain rule in the video, but I'll try to convince you at the end with a little argument if there's time. If the video gets too long, maybe I'll relegate that to an office hour, or maybe I'll end up making a separate video trying to give you some idea of why the chain rule works the way it does. And then one of our primary first applications of the chain rule, we know how to differentiate the natural exponential function, but I want to be able to differentiate any exponential function. So I want to be able to differentiate it no matter what the base is, even if the base isn't e. Okay, so let's get started. I wanted to start by kind of reviewing really quickly what differentiation rules we have so far. In this table, so some of these things, well, they're all rules, differentiation formulas, but some of them aren't really about how you combine functions, but rather special facts. So maybe let's just talk about them one at a time here real quick. This first one, the derivative of a constant is zero. It's because constant graphs have horizontal tangent lines. They're horizontal lines themselves. And then, of course, this is our very important power rule of differentiation. So it allows us to differentiate any power of x. We derived that the derivative of the exponential function is itself, certainly a very important fact. Constants can be pulled through derivatives. So if you're differentiating a constant times a function, you can just multiply the derivative of that function by the constant. And then these last four are rules about how differentiation behaves with respect to arithmetic. Yeah, what do I mean by that? The first one is saying that the derivative of a sum is the sum of the derivatives. So differentiation can kind of be interchanged with the arithmetic operation of addition. It can be interchanged with the arithmetic operation of subtraction as well. The derivative of a difference is the difference of derivatives. So those are arithmetic functions, or arithmetic facts rather, excuse me. Same for product and quotient rule. It's telling us how to differentiate two functions that have been combined with the arithmetic operations times and divides. The product and quotient rule are certainly more complicated than the addition and difference rule, but all four of those things that I've highlighted in yellow, those are sort of the four arithmetic operations, yeah? Plus, minus, times, and I hate to write it, but I'm going to divide. It's four arithmetic operations. Four operations that you can do on numbers. You can add numbers together, you can subtract numbers, you can multiply numbers, you can divide numbers. So you can do those four operations to functions because the outputs of functions are numbers. Okay, but functions have one more operation. Functions can also be composed because a function is more than a number. A function is a process, right? So we can also compose functions. What do I mean by that? If I take some function, say g of x, yeah, so if I take an input for it, g makes an output, g of x, that's a number. And I can then take that output and plug it into another function, f of x. So that's exactly what my notation is saying. I'm taking the number g of x and I'm plugging it into f of x. And that two-step process, x becomes f of g of x, is called the composition of f and g. And it's written like that. Yeah, f composed with g is how you read this on the telephone. F composed with g. It's a two-step process. First g goes, then f goes. So we typically use words like that, first, or it's because of this notation over here. We call g the inside function. It's the inside function. It goes first. It's very important to remember that when you're given an x in a composition, the function that goes first is inside in the sense that it gets plugged into the other function. Compare that to the role that f is playing here. F is usually called the outside function. It's the function that goes second. You apply f to the output of g of x, right? So a composition kind of has an inside and an outside. And this chain rule is all about how do we differentiate such a thing? If I've taken two functions, both of which are differentiable, f and g, and I compose them together in this sense, I plug g into f, the Chain rule is the answer to the question, well, how do we differentiate that result? How do we differentiate that composition, this two-step process? All right. So as I said earlier, I'm not going to state it without proof, but let me reveal the chain rule, just clipped from your book, written much nicer than in what my handwriting would write it. So let's check this thing out together. The chain rule says if you take two functions, both are differentiable, and I'm going to use the same naming and color coding scheme, that G is my inside function, F is my outside function, yeah? So you can see that in this composition down here. They're plugging G into F. And the chain rule says that if F and G are both differentiable, G differentiable at X and F differentiable at G of X, then this composition is differentiable. The composition the author is denoting by capital F. And the way the chain rule works is you take the derivative of little f, the outside function, evaluate it at the inside, and then you multiply that by the derivative of the inside. All right. So it's kind of a complicated rule. You have to take the derivative of both functions, but you kind of assemble those derivatives like this. In the Leibniz notation, if you wanted to give separate values, if we called the outermost output y, so f of u is y, and then we call u g of x, so x is the innermost variable, and we're giving kind of a temporary name, then the Leibniz notation says that, well, the derivative of y with respect to x, dy dx, is the derivative of y with respect to u, that's your outside function's derivative, times the derivative of u with respect to x, that's your inside function's derivative. So this is kind of a nice notation scheme for it, because it kind of looks, if you just treat those derivatives like fractions, it looks like the du's cancel. Yeah, it looks like dy dx is dy du times du dx. It makes sense if you just pretended those things were fractions. I think we need to do some examples. That's what I want to do in this video. I don't want the video to get too long, but I want to do lots of examples. Before we do it, I like this. I won't do this very often, but I do like this illustration. So I also clipped it from your book, that when this is kind of the mechanics of the chain rule. When you're taking the derivative of this composition, this f of g of x, yeah, you take the derivative of f. If you can read the author's print there, you take the derivative of the outside function, but you plug in the inside function to that. So you take derivative of the outside at the inside, and then multiply that by the derivative of the inside. Okay, that's the mechanics of the chain rule. You take the derivative of the outside, plug in the inside, multiply by the derivative of the inside. It's very important that you know which one is which. Again, the inside function goes first. The inside function goes first. Let's try an example. Let me try to leave that note visible here. Here I've got a composition. I would stop the video right now if I were you and try to decide which function is inside and which one's outside. Yeah. To answer that question, if you want me to help you, the function that's inside is what you do first to the variable. So if I grabbed a number x and wanted you to evaluate this function, sine of x squared, the first thing you're going to do to that x is what? What are you going to do to the x? Are you going to take the sine of it first? No. The first thing you're going to take, what you're going to do to that x is you're going to square it. So that's your inside function. Your inside function is x squared. Yeah, it's what goes first. After you square that x, then you take the sine of it. So that's your outside function. Yeah, the notation is kind of nice. Sine kind of looks outside to me. All right. So how do we take the derivative of this with the chain rule? Let's just write our computation down here. So you have to take the derivative of the outside function. So you need to know, what is the derivative of sine? The derivative of sine is cosine. That's the derivative of my outside function. But what do I evaluate that at? I evaluate it at the same inside. So the computation starts off derivative of outside function cosine at x squared, and then you need to multiply that by the derivative of x squared. You can do this on the fly, but since this is our first time, I'm going to write it as two steps. So when I'm done, I'll write that I've got the cosine of x squared times, well, the derivative of x squared is 2x. And typically, there's no mathematical reason to do this, but we typically write constants and polynomials in the front. So I'm going to write my answer. This is what I would expect to see in the back of the book. Right, so there's my derivative of sine of x squared. It's 2x times the cosine of x squared. 2x coming about from the chain rule factor. Okay, pause it, soak it in, but I'm just going to keep going, trying to keep this thing short. Let's look at a different example. Here I've got a very similar function, yeah, sine squared of x. What's the difference between our previous example, sine of x squared and sine squared of x? What's the inside function here? Remember, for trigonometric functions, when you write something like sine squared, what does that exponent mean? This is just a notational way of saying sine times sine. So here in the sine squared of x, I've got the same two functions as in example 1, the squaring function and the sine function, but I've just changed who's inside. Yeah, I put the sine function inside this time. If you grabbed an x, the first thing you would do to this function is take the sine of it, and then you'd square that, right? So the thing that goes first is inside. So when we do this computation using the chain rule, okay, well, the outside function is the squaring function. So the squaring function's derivative is 2 times the thing to the first power. And what's the thing? It's the sine of x. So I leave that inside function there. So there's my derivative of the outside evaluated at the inside. And then I have to multiply that by the derivative of the inside, which is the sine function. All right, so in this case, what are we going to get? We're going to get 2 times the sine of x. Well, the derivative of sine of x is cosine of x. So our second example, the derivative of sine of x squared is 2 sine x cos x. It's 2 sine x cos x. This is just popping into my head. Maybe I'll ask some of you trigonometry experts out there. Do you know an identity? There's a double angle formula. You could rewrite that in terms of the sine of some other angle. Maybe I'll leave that as a challenge to you. All right, good. Let's keep going. Let's do some more of these things. I want you to practice this until it becomes second nature. You need to identify what's inside, what's outside, and then use the formula correctly. So here I want to take the derivative of the square root of x to the 5th plus 1. What was my sage advice for dealing with derivatives when you have roots involved? You want to write those roots as exponents. The square root is the 1/2 power. And haven't written it like that, can you pause it for a second and decide for yourself what's inside and what's outside? What would be the first thing you do to an x? If you wanted to evaluate this function, the first thing you'd do is take its 5th power and add 1. That's inside. After you do that, then you'd take the square root. That's the outside function. Okay, so the derivative of this thing, how should we proceed? We take the outside function's derivative. So I'm using the power rule. It's 1/2. I evaluate it at the same inside. So if I paused for a second, there's the derivative of my outside function at the inside, and now I need to multiply that by the derivative of the inside, which I'm going to keep writing this as an additional step, but you can do it on the fly. So 1/2 x to the 5th plus 1 to the minus 1/2. Well, the derivative of x to the 5th plus 1 is 5x to the 4th, right? So I can leave my answer like that, or if you want to clean it up a little bit, you can certainly rewrite the constants out front. 5/2, got an x to the 4th. If you want to write it in the original form, that x to the 5th plus 1 to the minus 1/2, you can rewrite that in radical notation in the denominator because the exponent is negative, right? So there's sort of a nice way to write that answer. Or if you like, you can put the 5 and the 2 in the well, it doesn't helpful to say that. You could write it like this. If you wanted it as a single fraction, it's 5x to the 4th over 2 times the square root of x to the 5th plus 1. Cool. Let's keep going. Let me check my watch here. We're 14 minutes into this thing. Can we do a couple of more? How about this one? This one I'm asking for a second derivative. Yeah. H of t is e to the t squared plus t plus 1. So what is the inside function here? So if I handed you a number t, if I handed you the number 2, what would be the first thing you did to evaluate h of 2? Yeah, I think the first thing you would do is calculate out what 2 squared plus 2 plus 1 is. Yeah, because then you'd make that the exponent that you would evaluate e. So your inside function here is what's up in the exponent. The outside function is the exponential function itself. It's always that for an exponential function. what's up here in the exponent is always inside for an exponential function. We were asked for the second derivative here, so we got to compute the first derivative first. So let's try it. H prime. What's the derivative of the outside? Well, the derivative of e to the x is itself. So when you take the derivative of the outside and you evaluate it at the inside, you just start by kind of copying what the function was. But now I need to multiply that by the derivative of the exponent, t squared plus t plus 1 prime. So there's the chain rule done, and now we just have to do the details. So we get, well, e to the t squared plus t plus 1 times the derivative of that polynomial is 2t plus 1. So there's your first derivative. Second derivative, we're going to do the same kind of thing. We're going to have to use a chain rule in this first factor. It's going to come up again, but what other rule are we going to have to use? We're going to have to use the product rule because we have the product of this exponential function and this linear function. All right, so now we're kind of combining. It's getting a little thick, but we can do it. So how does the product rule work? Well, you take the first function, undifferentiated, and you multiply that by the derivative of the second function. And then you add to it the other way around. So take e to the t squared plus t plus 1 derivative times the second function, undifferentiated. All right, and now we just have to do the differentiation details. Let me give myself enough room here. So I've got e to the t squared plus t plus 1. Derivative of 2t plus 1 is just 2, right, by the sum and constant multiple rule. And then, well, we have to differentiate this exponential function again. We just did it. E to the t squared plus t plus 1 is the derivative of the outside function times the derivative of the inside. This time I'm just going to do it on the fly. 2t plus 1, that's from our chain rule. And then I've got this other factor of 2t plus 1 that was going along for the ride. So you guys with me? This 2t plus 1 came about from, the one I'm underlining, came about from the second application of the chain rule. The other one was just the undifferentiated factor. Okay, and then we can algebraically clean that up, but I think I'm going to leave it like this. So trying to keep this video a little bit shorter. All right, so you can do some algebra there if you want to, but that illustrates the chain rule. I actually want to use this space to kind of write a more general formula. If you have some function, maybe I shouldn't call it f because of the chain rule formula. Let me call it h. If you have some function h of x, and it's of the form e to the g of x, this is what I was saying above. The g of x is always the inside function, and the exponential function is always outside. So the chain rule, there's sort of a nice pattern here. The derivative of such a thing with respect to x, it's always e to the g of x. That's because e is its own derivative. And then you multiply by the derivative of the exponent. Yeah. So this is a pattern that I would encourage you to sort of deeply internalize. That the derivative of an exponential function is itself times the derivative of the exponent. That's just a consequence of the chain rule and the fact that in an exponential function, the exponent is always inside. The rule, the order of operations say so. Okay, good. Let's try this one. What's the inside function here? I didn't give the function a name, but what would be the first thing you would do to the x if you were starting to process this? The first thing you would do if I handed you a specific value of x is you would compute the value of x to the 5th plus x plus 1. Then you would take the 100th power of that. Yeah. So the outside function is the 100th power. The inside function is that 5th degree polynomial. So the derivative of such a thing, well, the power rule says the derivative of the 100th power of something is 100 times that thing to the 99th power. That's the derivative of the outside function times the inside. And now, can I just do it on the fly? What's the derivative of the inside function? It's 5x to the 4th plus 1. And I'm just going to leave that like that. All right. So here I'm going to start doing this more and more. I won't write inside prime, I'm just going to write the result. And you can too. This will become easier for you once you have these patterns of the rules internalized. So at any given moment when I do a calculation like this, I'm not thinking about very much at one time. I'm just focusing on what am I differentiating and what is its derivative. Okay? Here, I'm going to scroll. This example, I wish I could kind of keep it all in one frame. Maybe I can if I shrink it just a little bit, but it's I don't like it. It's an example of this more general rule that anytime you're differentiating a power of something, let me use my same color coding, then the power function itself is the outside, and what you're taking the power of, the u in this case, is the inside. So the chain rule will always work like this, that you take the outside derivative, so that's your n times u to the n minus 1, and then you have to multiply that by the derivative of u. Yeah, or if you like it in more kind of traditional notation, if you're taking the inside, oops, sorry, the inside function, I color coded these backwards. Darn it, darn it, darn it, darn it. Let me start again. Maybe I'll try to edit this out of the video. Maybe not. Maybe I'll just leave it in as a surprise for you. But here, the inside function is the what you're taking the power of. Yeah, it's the u. So the inside. Come on, Tyler. The inside function is what you're taking the power of. So that inside function is the g of x. Yeah, you calculate g of x first, and then you take the derivative of that. So the exponent is the outside function. So the n times u to the n minus 1, that's the derivative of the outside times the derivative of the inside by the chain rule. Good. Okay, sorry about that confusion. Hopefully it makes the video more entertaining. So last thing, I don't think I'm going to try to include a proof of the chain rule here because I want to try to keep this thing short. But I do want to derive how to differentiate an arbitrary exponential function. So remember, for an exponential function, b to the x, there are some conditions on b. When you're looking at an exponential function, b to the x, the base b has to be a positive number, but we never allow it to equal 1. Yeah, so when you look at exponential functions, we don't look at negative bases, but we also don't look at the function 1 to the x because it behaves differently. And then this fact is just a fact about exponential functions. You can ask me about it in an office hour or look at some Khan Academy or review videos if you need to, but you can always express any exponential function in terms of the natural exponential function by this formula. Any two exponential functions are in some sense a scaled version of each other. So b to the x is always the same as e to the x times the natural log of b. And that's up in the exponent. You can derive that with logarithm properties. But for right now, I'm just going to move on. So we can take advantage of that and the chain rule if we wanted to calculate the derivative of b to the x. Because, well, if we want to take the derivative of b to the x, looking at this boxed formula up here, we can just differentiate e to the x times log b. Right? So what's the inside function? Let me try to get my colors right this time. The inside function is the exponent, and the outside function is the e. So when you take the derivative of this thing, you take the derivative of the outside at the inside, so that's this first part, times the derivative of the inside. Natural log of b is just a number, so when you're taking the derivative of that number times x, you just get that number. Yeah, so you end up getting e to the x log b times log b, but e to the x log b is b to the x. Yeah, so you can substitute e to the x log b back for b to the x, and that's the formula, and that's the one I'm going to kind of show a summarized version of. The derivative of any exponential function, it's kind of itself. The derivative of b to the x is b to the x, well, except you have to multiply by the natural log of b. Maybe let me remind you here, if you haven't already reminded yourself, that the natural log of the number e is equal to 1. Yeah, so that's why when we take the derivative of e to the x, we just get e to the x because this multiplication factor over there is equal to 1. So sometimes people say this is some evidence that e to the x is one of the best bases because you don't have to remember this multiplication factor when you go to take its derivative. The derivative of e to the x is just e to the x because the natural log of e is 1. Okay, real quick, just to illustrate it with some kind of computation, reminding you about some applications here. So let's try to find the slope of the tangent line to the function 3 to the x at the point 1, 0. Okay, so how does a differential calculus student think about the question slope of the tangent line? What's the translation of that? The slope of the tangent line is the derivative, and we want to evaluate that derivative. Sorry, this is a sloppy video. I didn't mean the point 1, 0. The point 1, 0 is not on that graph. I mean at the point 0, 1. F of 0 is equal to 1. Sorry about that. So it's fixed. So we want to calculate f prime of 0, basically. Yeah, the slope of the tangent line when x is 0, I want to calculate f prime of 0. Okay, well, f is 3 to the x, so our brand new formula that's still visible at the top of the screen there says that its derivative is 3 to the x times the natural log of 3. Yeah, so f prime of 0 is 3 to the 0 times the natural log of 3. 3 to the 0 is 1, so it's the natural log of 3. So the slope of the tangent line is natural log of 3. You can get out a calculator. That's a number that's slightly bigger than 1. Okay, so we're going to stop it there. I hope that you'll use the activities and the homework in the text to practice the chain rule and become proficient and confident at it. And thank you for listening.